Polaris is the most recognized star in the northern hemisphere. It sits almost directly above Earth's rotational axis, which means it barely moves while every other star in the sky appears to rotate around it. For centuries, sailors, explorers, and navigators used it as a fixed point of reference to cross oceans and deserts. From down here, it looks simple: one steady point of light, permanent, reliable, the kind of star that should be easy for modern science to understand completely. It isn't. The closer astronomers look at Polaris, the less it cooperates. Its distance is still debated. Its mass doesn't match its age. Its pulsation behavior has changed in ways no model predicted. And it may be forcing us to reconsider a tool that underpins our entire measurement of the universe. In this video, we'll break down what Polaris actually is, why it keeps defying our models, and what that means for how we map the cosmos. What we see as a single point of light is actually a triple star system. The brightest component, Polaris AA, is what we think of as the North Star. It's a yellow supergiant, 5.13 times the mass of our Sun and 46 times wider. If placed in our solar system, its surface would extend more than halfway to Mercury. Orbiting Polaris AA at a distance of roughly 1.74 billion miles is a smaller companion called Polaris AB. The two complete one orbit around each other every 29.6 years. Both Polaris AB and the third member of the system, Polaris B, are yellow white dwarf stars, roughly 500 times fainter than the primary. Polaris B circles the inner pair at an enormous distance, approximately 240 billion miles, completing one orbit every 40,000 years. For perspective, that's about 24 times farther than Voyager 1 has traveled in nearly 5 decades of flight. The close companion, Polaris AB, wasn't even directly imaged until 2006, when the Hubble Space Telescope finally resolved it from the glare of its much brighter neighbor. A star that humanity has navigated by for millennia turned out to be 3 objects disguised as one. The primary star, Polaris AA, belongs to a rare and scientifically critical class of stars called Cepheid variables. These are evolved stars in a specific phase of their life cycle that pulsate regularly, expanding and contracting, growing brighter and dimmer in predictable cycles. In 1908, astronomer Henrietta Leavitt discovered a direct relationship between a Cepheid's pulsation period and its true luminosity. The longer the period, the brighter the star. That relationship turned Cepheids into what astronomers call standard candles, objects whose real brightness can be determined just by measuring how fast they pulse. Once you know a star's true brightness, you can calculate its distance by comparing that to how bright it appears from Earth. A known light source that looks dim must be far away. A known light source that looks bright must be close. The principle is straightforward. The implications were enormous. Before Leavitt's discovery, astronomers could only measure distances out to a few hundred light years using stellar parallax, the apparent shift of a star's position as Earth orbits the Sun. Cepheids extend that reach to millions of light years. They became one of the most important rungs in the cosmic distance ladder, the chain of techniques that allows us to measure the size, age, and expansion of the universe. As the closest Cepheid to Earth, Polaris should be the anchor point for calibrating all the others. It should be the most precisely measured Cepheid we have. It should be the foundation stone. Instead, it is one of the most confusing. Cepheid variables are supposed to be predictable. That's their entire value. But Polaris AA has been doing things that no other Cepheid does. First, its pulsation amplitude. The difference between its brightest and dimmest points declined steadily from the 1960s through the 1990s, dropping from above 0.1 magnitude to below 0.05. Then it leveled off and held steady for several years. Then around the year 2000, it began increasing again. This pattern of decline, stability, and recovery has never been observed in any other Cepheid. Second, its pulsation period, roughly 4 days, was getting longer by about 4.5 seconds per year for as long as astronomers had been measuring it. That rate of change is extremely fast for a Cepheid and suggested the star was evolving rapidly through an unstable transitional phase. Then around 2010, the period stopped lengthening and reversed direction. It began getting shorter. No one has a confirmed explanation for why. One hypothesis involves Polaris AB, the closest companion. Each time the two stars approach their nearest orbital point, the gravitational interaction may be disturbing Polaris AA's pulsation dynamics, but the mechanism remains unconfirmed. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. For a star visible to the naked eye from almost anywhere in the northern hemisphere, Polaris is surprisingly difficult to pin down in terms of distance. Part of the difficulty is that Polaris is extremely bright, which can saturate the detectors on precision astrometry satellites. Part of it is that Polaris AA pulsates, which introduces variability into brightness-based distance measurements. And part of it is that the close companion AB adds its own light to the signal, complicating efforts to isolate the primary star's properties. The Hipparcos mission in the 1990s placed Polaris at roughly 434 light-years. The more recent Gaia mission measured approximately 447 light-years. These numbers are close but not identical, and both carry uncertainties that leave room for significant revision. Distance matters because nearly every other property we calculate for Polaris depends on it. Mass, radius, luminosity, age are all derived from models that require a known distance as input. Shift the distance and the entire profile of the star shifts with it. Even with the best available distance estimates, Polaris AA doesn't align with stellar evolution models. Its observed mass appears lower than expected for a Cepheid with its luminosity and pulsation period, and it appears to be far younger than its distant companion Polaris B. If the two stars form together and their shared gravitational binding strongly suggests they did, they should be the same age. But current estimates place Polaris at roughly 50 million years old, while Polaris B appears closer to 2 billion years old. That's a discrepancy of almost 2 orders of magnitude. Several explanations have been proposed. One is that Polaris B is not actually gravitationally bound to the primary system, a line of sight coincidence rather than a true companion. But the evidence for physical association is strong, making this explanation unsatisfying. A more compelling hypothesis involves stellar mergers. In dense stellar environments, binary star systems sometimes collide and merge, producing a single star that appears younger, more massive, and hotter than its actual age would suggest. These objects are known as blue stragglers, first identified by Alan Sandage in globular clusters in 1953. If Polaris AA is the product of a past merger, 2 older stars combining into one apparently rejuvenated star, it would explain the age gap with Polaris B. The merger hypothesis is speculative, but it demonstrates how deeply the Polaris system changes our understanding of how stars evolve. There are additional complications. Stellar rotation, which affects a star's internal structure, surface temperature, and pulsation behavior, is extremely difficult to model and is often omitted from evolutionary calculations. For a star like Polaris AA, that omission could introduce significant errors. Mass loss through stellar winds or companion interactions is another factor that remains poorly constrained. And 2024 observations using the Chera interferometric array detected large star spots on Polaris AA's surface, consistent with a magnetic field that could independently affect pulsation dynamics. All of these unknowns converge on a single concern. If we cannot accurately model Polaris, the nearest and most accessible Cepheid, then our models for more distant Cepheids may carry similar, unrecognized errors. And since Cepheids are one of the primary tools for measuring cosmic distances, any systematic bias in how we model them would propagate upward through the entire distance ladder. That has direct implications for one of the biggest open questions in cosmology, the Hubble tension. Measurements of the universe's expansion rate using Cepheid-calibrated supernovae produce a value of roughly 73 kilometers per second per megaparsec. Predictions from the cosmic microwave background give approximately 67. If the Cepheid calibration is off, even slightly, It could shift one side of the equation enough to matter. Polaris isn't just a navigation star. It's a test case for whether our most fundamental distance measuring tools are as reliable as we think they are. Earth's rotational axis wobbles. The phenomena is called axial precession, and it traces a slow circle in the sky over a period of roughly 26,000 years. Right now, the north celestial pole points very close to Polaris. About 14,000 years ago, it pointed toward Vega. In another 12,000 years, it will return to Vega again. Polaris's tenure as the North Star is temporary on astronomical timescales, but for the duration of recorded human history, it has occupied that position, and for the foreseeable future, it will continue to. What has changed is what we ask of it. For most of human history, Polaris was a navigational tool. Today, it's a scientific test subject, one that keeps delivering results we didn't expect, contradicting models we trusted, and raising questions about whether the instruments we use to measure the universe are as calibrated as we assumed. The next major data release from the Gaia Space Telescope is expected in mid-2026. It may finally narrow the distance uncertainty enough to resolve some of the contradictions, or it may deepen them. Either way, the star we've relied on for centuries to tell us where we are is now forcing us to reconsider how much we actually know about where everything else is. Polaris burns at thousands of degrees, and billions of stars like it fill the universe. Yet, the space between them is almost unimaginably cold. That contradiction is stranger than it sounds. Watch, why is space so cold when the sun and billions of stars are so hot, to find out.